Quantum computing via cloud access feels global, but there are reasons to have these machines located in a particular region. Oxford Quantum Circuits released a quantum computer named Lucy that not only helps customers with regulatory concerns, but also brings an exciting new type of transmon technology to the industry. Find out more about the coaxmon approach to building QPUs in this episode of the Post-Quantum World. I'm your host, Konstantinos Kragianis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is Chief Technology Officer at Oxford Quantum Circuits, Simon Phillips. Welcome to the show.
Thanks. No, it's great to be here.
Yeah, and I was looking at your background, and it seems like an interesting path you took to quantum. So I don't know if you just want to spend a moment filling us in on that.
Yeah, no, absolutely. I think I'm probably one of the few CTOs in the quantum computing space that spent most of my life making video games, actually, was my history. So yeah, so 27 years ago, I start losing count now, I started off as a video games programmer, actually. And it is relevant. I'll kind of talk about it a little bit, but hopefully the relevancy will come through. So I started off as a machine code programmer back in making Amiga games and writing 68K and things like that. And over time, kind of really got into the technology side of video games and then running businesses and things like that, and really seeing a load of different emerging technologies coming through what used to be kind of a bedroom hobby, and it kind of grew into one of the world's largest kind of markets now, largest industries, and kind of sort of learned a lot of different things over time. And anyway, sort of cut a long story short, I met Alana probably 5 years ago, I think 5 or 6 years ago, just before she was asked to come into OQC as CEO. And we got talking about what we're up to and making video games. And there was at one point I did ask if she'd want to come and work for me, and then the kind of tables turned and things. But I was speaking to her when she started with OQC, and I kind of have this intro about video games where I genuinely thought we could change the world with video games. And after a fun conversation with Alana about quantum computing, she convinced me that actually I should come and join her over here. And really for me, there are so many similarities with what we do at OQC in terms of and quantum computing in general, in that it's such an emerging market, right? So there's things that we're doing that have just never existed before. There's business models that have never existed before. There's technology that's in such an infancy that we know is going to scale and become really, really useful. And all of those things kind of feel like things I've done in video games in the past, right? So when 3D games first came out, and someone dropped a PlayStation on my desk when I was a teenager, and we made 3D games, and when free-to-play gaming came out, it felt like madness at the time. You'd spend $10 million making a video game and then give it away for free. But actually defining those business models and how you deliver that technology to consumers is really what we're seeing now in quantum computing. But yeah, so I don't have a background in physics. I'm fortunate enough to have an amazing technical team here at OQC. So we have a number of quantum leaders in various fields. We have our connections with Peter Leak and the University of Oxford and his Leak labs there as well. So we kind of got a lot of the really technical science bases covered. And my job really is to build this with a strategy that's kind of bold enough to deliver this technology to consumers. And that's really, really exciting for me.
Yeah, emerging tech experience is very important in an emerging field like this one.
Yeah, and being quite brave as well. Working in video games for years has taught me to be quite brave. And really, one thing we say a lot at OQC is we've got to stop being British about this, right? We've got to be bold. We've got to be ambitious. We've got to be realistic, of course, but yeah, just really being brave a lot of the time as well.
I like that. Stop being British. I've never heard that expression. That's funny. And in the early days, I don't know if you remember with the first KissKit tutorials, some of them were games.
That's right.
So
yeah.
Those must have looked so primitive to you, right?
I really enjoy looking at Chasm code at the moment. Just reminds me of being a teenager again. It's and I really want to remember these days now where it's easy enough to kind of look at an entire circuit in assembly language and understand it, because in a handful of years this is going to be unrecognizable again.
Oh yeah, the depth is going to be wild as the machines are able to handle these circuits. So tell us a little bit about Oxford Quantum Circuits.
Wow. So what an exciting place it is to be at the moment. So we're really fortunate. We've got our core technology. So we spun out from the University of Oxford in 2017 from a core piece of technology invented by Dr. Peter Leak, which is the coaxmon, right? So this is a 3D integrated solution for transmon superconducting technology that takes it back to first principles about what if we could do away with all the things that are sort of fundamentally limiting coherence and kind of noise and crosstalk within quantum circuits? How would we redesign it if we started from scratch? And Peter Leak came out with a coaxmon. So really, whatever that is now, 5 years ago, it was a patent, a piece of paper, and some theoretical ideas and some things from the university. And we've spent the first 4 years, maybe 3 or 4 years, really bringing that technology out of the university and learning how we can recreate it and how we can actually start scaling it, and how we can engineer it to be what we all want superconducting circuits to be, right? So this kind of low crosstalk, high coherence platform for scaling quantum computers. And we were doing really well spinning that out of the university. Then COVID came along and forced us to really spin it out of the university when suddenly we didn't have access to facilities and things like that. So we very rapidly built the team up so we could start fabricating our own coaxmon style devices using university kind of recipes and things, but without the reliance of the university, which was really important when we started growing the company to be its own kind of commercial entity, right? So we'd got the basis of it, and we were able to very quickly demonstrate that we could not only create like a multiple qubit processor, but it's an actual processor. So we're talking about fully connected qubits, and we could demonstrate that. Then we kind of had what were side projects and are now massive technical pillars of the company. So we build all of our control hardware from scratch as well. We design and build all of our control hardware, which felt crazy when we started it. Now, there's a lot of technical advantages to doing that. Similarly with our own compilers, optimizers, cloud infrastructure, and all the things that go towards that. Where are we now? We're in 2022 now, so it was kind of 2021, right, when we launched Sophia, which was our 4-qubit processor that was our full end-to-end stack. So that was a third-party customer delivering a piece of code over our cloud infrastructure that used every part of OQC's technology to deliver results at the back end. And that was a really thrilling time. And we did all of that within like 4 years. That was less than a year ago. And then since then, we kind of scaled the processor up to 8 qubits, 8 fully connected high coherence qubits, and launched on AWS as well. So that rate of progress has been quite staggering, actually. But yeah, and then it's all really down to this core pattern that we've got around the coaxmon that allows us to scale without kind of introducing more crosstalk and things like that. So yeah, it's been wild.
Before we start talking about the new machine, a little bit about the coaxmon and the processor, I guess, would be in order here. So I guess if you look back at IBM's first transmon processor, it's flat, right? And it was just these like little snaking leads, and you had these 5 qubits, and you had to try and get them to talk to each other. And how would that compare if the audience wanted to visualize a coaxmon processor? So if you have 8 qubits, how are they arrayed? Like if you just wanted to try and capture an image.
Yeah, you've got the same key components, right? So you've got your qubit, your resonator, and you kind of readout lines and all that sort of thing. But what we do is we arrange them in complete 3D. So this is the kind of the core pattern. So rather than having everything trying to fit in a 2D space, and then you're trying to basically maximize that 2D space out, so you're keeping your wires away from your qubits and you're trying to control the environment, we kind of bring it all in 3D. So we have it looks really simple, and I hate to call it really simple to the entire fabrication team because there's a lot of hard skill that goes into it. But we do 2-sided fabrication. So we have qubit on one side, and then we have a resonator on the other side. And then our kind of control lines come in from the top and bottom. So the whole thing is stacked in 3D, basically. And the real magic is we never galvanically bond to the chip itself. We use capacitive coupling to go through the qubit and resonator. And what that really means is everything is limited to this plane here. So the crosstalk is minimized. Any kind of, the surface of the chip itself is so simple. You've just got a qubit on the top and a resonator on the bottom. So we can build out really complicated arrays of qubits and different connectivity patterns without worrying about where all the control wires are going and things like that. So it's a really clean, neat, very simple solution to quite a complicated problem.
So you can visualize it almost like each qubit is an invisible cylinder with the qubit in the center and the controls on the top and bottom, sort of. And then you can have as many of these invisible cylinders close by as you can.
Exactly, yeah.
So that's where the 3D comes in the control piece. It's not like qubits are floating higher and lower.
The great thing, because it's all capacitive coupling and there's no bonding, I mean, there's so many different technological niceties. You could call them advantages, but really the niceties in that we can create an environment where we can open up our sample holders, we can pull the wires away, and we can change the chip because we don't bond to it. So when we're in R&D, we can very quick R&D without having to kind of use, bump bonds or flip chips or, all those kind of complicated things that go on, I guess, would go into a normal kind of 2D architecture to get around wiring issues. So it's really pure and simple. It's quite cool, I think is probably the way to say it.
Yeah, it definitely sounds cool. So this 8-qubit processor now, would you consider this a unit going forward, like a computing unit? So like with IBM, their newest processor, it's 127 qubits.
Right.
And how are they going to meet their roadmap? Well, they're going to put 4 of those down, and then they're going to put down 10 of those, So is it going to be something like that where you're going to have this one little chunk of 8, or are you still completely flexible?
Yeah, so there's a number of bits of technology there. So again, because of the capacitive coupling, we're able to do really neat like chip-to-chip modularity. So we can capacitively couple through a qubit and a resonator. We could actually put another one on top and do 2 qubits stacked on top of each other. So when it comes to building modularity, it's, again, I do use the word straightforward. Nothing's really straightforward, but in the grand scheme of things, it's relatively straightforward for us to build out this kind of modular unit. But we're nowhere near at the limits to have to do that kind of thing yet. We can go much, much bigger before we need to go modular. Bearing in mind that as we scale our processes in 3D, it's kind of getting linearly larger. So every time we add a bank of qubits, they're not quite in a grid, but if you imagine a grid getting bigger, so we could add, n number of qubits for just getting slightly larger. We're not getting exponentially larger like a 2D setup would be with its kind of wiring fanning out. So we can go really large before we need to go modular, which is really quite smart actually. And we run into more engineering challenges than we do kind of QPU challenges before we have to go chip to chip. But the coaxmon really allows us to do some really neat kind of stacking of chips and tiling of chips. So we're pretty excited about when we get into these kind of real large scale systems actually.
Okay, so you're still a while away from having to do like multi-core, the equivalent of multi-core.
There's some good experiments we can do with it. We can even put connectivity patterns, on layers, right? So we can have a pure array of qubits, and then we can have different connectivity patterns that are kind of laid on top if we want to do very, specific experiments or something like that.
Mm-hmm. I'm assuming there's more benefits than just space saving. Have you tried to measure these 8 qubits against the competition? Like, do you use benchmarks, like something from Supertech, like Supermark, or do you experiment with like just quantum volume and that kind of thing?
Yeah, quantum volume is a really important metric for us. So we know inherently in the design we have, sort of really leading low crosstalk between the qubits, which is obviously important as we start scaling and we don't want to start compounding errors. And we kind of have naturally high coherence based on the simple design and the fabrication design as well. And we've seen some experimental QPUs and some work that's been done with the University of Oxford that are getting really high, like T1 and T2s, which is really exciting. Mm-hmm. By the time we distill the whole process down and we try and make, I'm going to say inverted commas, a usable 8-qubit processor, not all of those parameters kind of filter down, but we're really excited by the potential of it. So yeah, we use quantum volume as a kind of basic benchmark, if you like, and we're pretty pleased with where we are considering the life cycle of our processors. And I know when we launched on AWS, there was an independent paper launched that had some basic benchmarking done, and we were relatively high up on there compared to some people that make superconducting circuits that are much more mature than ours, let's say. But so we're pleased with the performance, and it's getting stronger all the time. So,
are you comfortable sharing what the quantum volume is of Lucy?
Yeah, I think we're kind of publishing. I mean, we're still in the sort of 2 to the 2, 2 to the 3, but we're in the world where we're going from 2 to the 2 to 2 to the 3 just based on calibration. So there's no specific hardware changes. So again, bearing in mind we've got the full stack. So we've gone from, our kind of, our software layer, our compilers, shaping pulses or tweaking the control hardware. We're still able to find these real low hanging fruit, and we often kind of not joke about it, I think it's probably the wrong word, but there's so many areas to attack, right? You've got to pick the right ones for the roadmap to say, right, let's progress down this road. But we're fairly confident that we'll continue to make quantum volume gains within our 8-qubit processor. And as we move on to our larger scale processors, we'll get the same or better volume as we go forwards because we never change the architecture, right? So it's the same unit cells, just larger and larger. So we're not dealing with complete new architectures like you might find in a 127 qubit processor, for example, where there's extra challenges that come in there. We're kind of really seeing this same or better performance gain as we add more qubits.
Do you have a sense yet of what your roadmap might be for a couple of years? Like, do you see it like this year we just add more of these imaginary cylinders? And I'm sorry if that's,
Yeah, no, it's
if I
great. That's
shouldn't
absolutely great.
overuse that. I just want the audience to understand. And then would you then say that, oh, next year now we're going to start stacking more on top, like you said, a whole other layer? Did you give thought to that?
Yeah, definitely. And I think, I mean, we have so many different variations of the roadmap, just in terms of from a pure quantum volume point of view. We've got a good idea of where we want to get to, and qubit count where we want to get to. And then, ultimately what that's going to distill down to is, sort of quantum volume and error rates and things like that we want to tick off. But really, the one that kind of reinforces that as well is the kind of infrastructure and commercial roadmap that we want to really tie these things together. So what our aim is as the technology gets better, the kind of, I guess, the ability of our customers, the learning journey that customers might be on is getting better, and infrastructure is getting better. So in all those three things really need to come together in a number of years' time to make sure that people are learning how to use quantum computers today at 8-qubit level. And I go back to talking about programming assembly language and understanding the fundamentals before it gets too complicated. So I think if you can start programming an 8-qubit processor today with a modest quantum volume, as that grows, you're really got to grow into it in terms of the journey. But at some point when you're ready, you want to have much higher quantum volumes and higher circuit depths and things like that, and the infrastructure to use it as well. By infrastructure, I mean the feature set. So moving to OpenQASM 3 or whatever the kind of customer journey is as well. So we've got a lot of different things to kind of squeeze up this stack, and we remind ourselves a lot that we're a quantum computing as a service company, not a qubit processing manufacturing company or a hardware. We do everything to make quantum computers a service. So it's every part of that stack is just as important as the rest.
Okay, so I'd love to hear a little more about Lucy. So it launched on AWS in the UK.
That's right.
Is this the only way to access it right now?
No, so we have our own private cloud access as well. So always part of our roadmap was public access, which we call it public access via AWS. So we don't need to have customer interactions. You can just log right on. You can experiment and start using the processor, which is fantastic. But we also have our kind of private cloud access. So we have a cloud API that we can work directly with customers on, and we're seeing a lot of attraction there as we take on the role of like an on-ramp for learning how to write quantum algorithms or learning how to use quantum computing. So it's more about the relationship with the customer and going, right, how do I start thinking about quantum algorithms away from classical algorithms, or what sort of problem should I be looking at? So we built our cloud infrastructure around our private access. So I could give you an API key now and you could log on and we could do a deal between us for access and kind of consultancy. You work with our engineers, you work with our BD team and things like that to help identify the sorts of things that you should be looking at as a business preparing to be quantum ready.
So there's a way to select this soon, maybe as like a back-end target on Penny Lane?
Absolutely, yeah. So we want to be really customer led in those integrations. There's so many cool ways that we could allow access, but really, if we can see a need for a customer to say, actually, I'd like to access your computer like this, we build out those kind of integrations, if you like. But again, the real advantage for us, because we've got the whole stack, we can choose at what level you interact with the computer, which is pretty cool.
And I noticed in the setup with AWS UK, you have it's very region based, right? So you have like hours of the day that it's accessible to that. And is it given priority for AWS for those hours, like those UK business hours? Or so like, for example, if you had a US customer, would they then be better off doing it at a different time period so that way they don't step on the toes of?
It's kind of I have a bit of a bugbear with windows and queues and things like this. We always say, the theme parks are great apart from all the queues. So one thing, we kind of have a clear vision for quantum computing in the future where it should be just seamless to the user, right? So almost to the point where you don't care that it's a quantum computer. You just want to solve a problem. You don't care where it's located. You don't care when, what priority you've got. It just works. So that's really the long-term goal, is to move away from like windows and queues and prioritization. Today, we offer a number of hours to AWS customers on the system every day. And if that is completely full up, you sit in a queue, and when the window opens, you kind of go again. And it sort of cycles like that. But we really want to move away from that model long term and find a way that we can just have full accessibility. That comes with its challenges, right? So there's not that many QPUs. We're fortunate enough that we have several live QPUs, but we're not in a world where we've got thousands of QPUs online like you would have a CPU or a GPU. But that's kind of the way it's going. But yeah, today there's a window through AWS. if you're a private customer, we can either do windows or deprioritize time as well. You might not care to have like 2 or 3 hours of compute time. You might just want to run what you want to run when you want to run it. So we'll kind of be able to set up windows like that. But yeah, today it's quite rigidly based on time zones and windows, but we want to move away from that.
And are there other reasons why it's important to have it available in the UK to people in the UK?
Yeah, massively at the moment. I mean, there's a huge topics around like data sovereignty and data security, and even down to things like GDPR and things like that. So a lot of people we talk to, any data can't cross borders. So it's really important to know where the computer's located, how the data's handled, where it's physically stored. So even to the point where we might go over a public cloud, but people want to know exactly where their data goes, like full traceability there. So there's a real reason for those kind of regionalizations. That's going to change a little bit over time, I think, but by and large, people still really want to know what regulations their data is bound by when it's processed and stored. So from that point of view, the region is really important.
It also makes me wonder if there's like somewhat of a misunderstanding about how quantum computers work when people worry about that. Like what gets sent to a quantum computer, it's so meaningless. It's not human readable or usable in any way, shape, or form. Your
right.
approach, is it?
Yeah, no, it is pretty bonkers, but it's usually one of the first things that people might ask, right? So where is the data stored? Where's it being processed? Can we come and poke it? Does it really exist where you say it does? And all that kind of stuff. But yeah.
Because you're not putting someone's social security number or something in a quantum computer. It wouldn't know what to do with it. It'd be like, oh,
absolutely not. And really in some ways, it's really good practice, right? To make sure that this infrastructure is in at this early stage, but kind of people being realistic about the sorts of things that you can run on a quantum computer nowadays compared to 3 or 4 years time. But yeah, I guess it's good practice to kind of get this stuff in place now, I suppose.
If you would imagine Lucy, would you say that, we'll call her she right now, would you say that she's somewhat between, so like IonQ, Quantinuum, they do trapped ion, and that's like sort of fewer qubits, but they're touting like super high fidelity and quality and all that, right? That's and connectability, gateability. And then you've got like IBM with 127, but the quantum volume's kind of low, and good luck getting all those qubits to talk to each other right now. It's just not going to happen. So how would you visualize Lucy in that like two extremes? Like how does she fit in?
Yeah, I mean the ultimate goal is all of those things, right?
Course,
so with superconducting circuits, I mean, the first thing we've got is the kind of engineerability, right? So when we talk about, the types of connectivity we can build in or the types of IP we can generate, we spoke briefly about kind of, flipping connectivity patterns on or, changing things depending on algorithms. That's pretty neat. And I think really the big differentiator for us in superconducting circuits, again, back to the coaxmon, that we can simulate, and we know from demonstrations that we can achieve really high coherence and low crosstalk, which is really important. So as we start moving into the real high fidelities and trying to move from what we're calling noisy into more fault tolerant, we know we've got a really good base to start with in terms of having the pros of the engineerability of superconducting circuits right up into getting into these like super low error rates, and some other cool things with the simplicity of the top surface fabrication when we start talking about building in error correction schemes and things like that. So we're pretty buoyant. Obviously, we're buoyant for superconducting circuits, and we think we've got a number of long-term advantages which some of the other technologies kind of have today. So yeah, we remain really positive about where Lucy's going to go, or Lucy's, I don't know, are they going to be siblings or children, whatever we're going to kind of
other physicist names, or if you like Dracula, it could be Lucy and Mina. I don't know.
Yeah, but it's so nice to have a really simple core technology where we can see the engineerability and the sort of things we might want to put on one of our chips that we know traditionally would be quite hard with a standard kind of superconducting transmon approach, because there's a lot of complications.
Okay, so trying to visualize those focuses. How would you say the pricing per shot compares for Lucy, let's say, to IonQ or something like that?
Yeah, I don't know. I mean, it's
complicated. I know
this is what everybody's learning at the moment, right? So I think I don't think price is a barrier at the moment, and I definitely don't think price should be a barrier. I think we want to grow the ecosystem, right? Part of what we want to do is put quantum computing in the hands of people, so you can start experimenting and start growing the knowledge base within what ultimately will be customers, these multinational companies with huge data requirements. So we don't want to block anyone out on price at the moment. We're on a big R&D stream anyway. So it's not like we have a business model that says, hey, we're going to be profitable within a year. That's just not going to happen at the moment. There's not enough, per shot demand to do that today. But what we want to make sure we're doing is giving a fair value and really kind of placing Lucy in the marketplace compared to other technologies where we think it should be. So that's our kind of main thing at the moment, in that this seems to work. I mean, ask me again in a year and I'll have a lot more data, right? But and it's changing a lot. Going back to the emerging business model thing that we saw in the video games, right? This is changing quite rapidly as demand's shifting from maybe just sort of academics and experimentalists into actually having businesses starting to push for business value and things like that. So it's maturing quite quickly. But yeah, I don't think there's a lot of science in this area.
Yeah. And the one big thing I'd like to see is every company having a calculator, because people get really nervous. I've said it a few times on the show. When we're getting ready to run something on a real machine, it's like, is it going to be $20, $1,000? Like sometimes you're just not sure it's going to happen,
This is sort of like one of the motives behind the private cloud offering as well, right? So we can sit down and really set expectations to go, look, we're going to give you X amount of compute time. Don't worry about the cost. We'll see. We'll kind of benchmark, right? We'll start benchmarking what you might have to spend to do X, Y, and Z on the computer or something like that. So there's, that's partly the driver behind the private access as well. So we can start learning what the business model should be.
And one of the benefits to going through something like AWS is this ability to visualize a complete workload. You start with classical, you go to quantum, you go back to classical. Yeah. And AWS did some work with hybrid jobs. I don't know if you wanted to maybe explain a little bit about that.
I mean, it's brilliant that they're moving in that direction, because ultimately, to get to this vision of seamless quantum computing, we have to have fully integrated hybrid jobs. And there's some things that quantum computers just can't do or are not very good at. So we need to make sure we've got the classical workload balance there. And there's a lot of complications with that. But there's some deeper technical designs that we've made in our kind of process and architecture that allows Lucy to be quite well suited for hybrid jobs. There's still a lot of work to be done. There's a lot of data flying around. Well, comparatively, there will be a lot of data flying around. There's only kind of 8 bits of data flying around at the moment, right? But ultimately, we need to make sure those two things are really synchronized. But hybrid workloads are really fundamental to getting not just circuits, not just algorithms, but full applications running on QPUs and CPUs and GPUs, right? All three types of technology have a place to run together to get the ultimate solution for a customer. So hybrid workloads will be ultimately driven by customer demand when they say, this is the problem I want to solve. And then we can go, these are kind of the quantum parts, but these are the classical parts. And they just want this to be seamless and just work like they do anything else. And like we would do, when cloud computing first came into video games again, you could just spin up all these different services. You could spin up a GPU, spin up a CPU, and now you can spin up a QPU. And you just want those things to kind of interlace and work seamlessly. But we might be a few years away from getting this real-time seamlessness because there's a demand element, right? There are a lot of CPUs in the world, and there's a lot of them idling in a lot of data centers. There's not that many QPUs sitting around idling.
Becomes the bottleneck.
So that's the next problem to kind of marry up there.
Did you have to do anything special, either somewhere on the stack, for example, to work with AWS on hybrid? Did they need any special requirements from you?
There was some really, I'm going to say, some good fortune and some kind of, I guess, some foresight and design as well, in that there are some special requirements to get efficient hybrid workloads. And fortunately, our stack was built in a certain way that meant that they married up quite well to start with. Yeah, of course, there's some modifications that have to happen, but we were always building this stack with our eyes wide open about how this is going to work going forwards. And speaking to AWS during the integration period, it was like, right, we've got this, you've got this, look at that. They almost line up perfectly. So we're pretty excited and pretty timely, right, as well, as they're launching their services around the same time that we came to AWS as well.
Yeah, I thought there was some good synchronicity there. And
yeah, definitely.
Yeah, and as we're winding down, will OQC be working on anything other than just like processors in the future? Is there something you want to hint at, something listeners can be on the lookout for?
I think, there's always things to hint at, right? I mean, we just remain exuberantly excited about the future. But I like to say, for us, it's not just about building the processors, and it's not just about building the whole systems. It's about looking at it through the eyes of a future customer and going, right, by the time the customer's ready to use a quantum computer, we want the technology to be there. We want the infrastructure to be there. We want it to be seamless, right? We don't want any barriers to entry. By the time that, bank X, Y, and Z has built their quantum information team and they're ready to go, and they go, right, where's this quantum computer then? It's right there, ready to be used at the right level. So there's a lot of projects that kind of go to bring that together. And one strand of that is building these kind of, high coherence, low error rate QPUs, but there's a there's a lot of things in that stack that
Yeah.
lead us to this vision of kind of seamless, quantum computing in the future.
Yeah, I think the stack is sort of like its own iceberg. Like people don't realize how much more goes into these than just the processor, everything around it.
Yeah, I mean, it makes my job super exciting when it comes to the strategy of trying to harness all of these different teams and expertise that we have here at OQC, bring some extra partners in there that might do some things better or more economical than we can do. It's a big volume of work, right? But it's super exciting when it all comes together.
Yeah, thank you so much. I hope to maybe have a chance to poke around with that machine a little bit in the off hours for UK.
You're always welcome.
Yeah, yeah. Thanks for coming.
Great. No, thanks. It's a pleasure to talk to you.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today in case things got too nerdy at times. Let's recap. Oxford Quantum Circuits, or OQC, spun off from the University of Oxford in 2017 and has been working on bringing coaxmon technology to the world. Coaxmon is a 3D integrated solution for transmon superconducting quantum processing units, or QPUs. The hope is to achieve low-cost, scalable, stable qubits. The company builds all its own control hardware too, and the software stack. Coaxmon processors are similar to other transmon processors in that the same support electronics for the qubit, like a resonator, control lines, etc., are present. However, in traditional transmon chips, those elements have to be routed on a flat 2D plane to each of the qubits. In coaxmon, these control elements are instead incorporated above and below the actual qubit itself. If you imagine each qubit as a cylindrical unit, you can see how it would be easier to fit more of them closer together by taking advantage of that three-dimensional space. Complicated arrays and patterns can be built without worrying about how to route control circuitry to the qubit itself. OQC considers itself a quantum computing as a service company, not just a qubit manufacturer. They're concerned with all layers of the stack. Their first 8-qubit machine is called Lucy. Lucy can be accessed by Amazon Braket, but OQC also has a private cloud that allows direct access. You can use an API key and select Lucy as a target. In the UK, there are hours of availability for Lucy to minimize wait times for local companies. Customers in other regions can access as well, and the hope is to optimize queues based on time zones. Having a machine in the UK is important for companies concerned with GDPR and not letting information cross borders. Even though quantum computers don't technically access sensitive information, the concerns are still there. Amazon has been working on hybrid jobs. Here, AWS classical hardware is used for parts of a task where it will excel, while quantum computers are handed parts of the task where they will excel. Lucy is ready to work with this solution today, as OQC's stack has already met many of Amazon's requirements for hybrid jobs. This hybrid approach is where quantum and cloud will really come together synergistically in true production use cases in the future. That does it for this episode. Thanks to Simon Phillips for joining to discuss Oxford Quantum Circuits and their new type of quantum computer. And thank you for listening. If you enjoyed the show, please subscribe to Protivity's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on Twitter and Instagram at Constant Hacker, that's constant with a K, hacker. You'll find links there to what we're doing in quantum computing services at Protivity. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protivity.com or follow Protivity Tech on Twitter and LinkedIn. Until next time, be kind and stay quantum curious.